We are going to learn Gauss's law. And you know how? By watching this quiz. There are two teams over here. The participating teams are Team Coulomb and Team Gauss. And the quiz has 5 questions. Let's see which team wins the trophy. Now the first question is to find the electric flux through this spherical surface if a charge of 1 microcoulomb is placed at the center of the sphere. If you're solving this, you can pause the lesson and think, let me see how Team Coulomb is solving this question. They are using the definition of electric flux, and you know that the total electric flux phi is equal to integral E dot dA, where E is the electric field and dA is the area element. And the direction of the area element is an outward drawn normal. So if this is the surface, then this is the direction of dA. Now this is because if you recall, area is a vector, and in case of a closed surface, the direction of the area is given by a normal drawn outwards from the surface. I have discussed what is electric flux in a lesson titled Electric Flux, so please see it if you do not remember the definition of electric flux. Now coming back to the question over here. So if you want to use the definition for electric flux, then we need to first find the electric field at every point, and the electric field times the area will give us the total flux. Now for a point charge, the electric field at the surface of the sphere is going to be E is equal to kq by r square. Actually the electric field at a distance r from it. So the surface of the sphere is at a distance r from it. So the electric field will be given by kq by r square. Now for all points on the sphere, the electric field same because they are all at the same distance r. Now if you look at this integral, then phi can be written as, you can put E outside the integral because the electric field E is the same everywhere, and we are left with integral dA. So which gives us kq by r square times integral dA, and integral dA is the total area of the sphere, which is 4 pi r square. So now this works out to be kq times 4 pi, and k can be written as 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of the medium, times q into 4 pi, q over epsilon naught, and now plugging in the value of q, which is 1 microcoulomb, and epsilon naught is a constant, and it has a value of 8.85 into 10 to the power minus 12, and the units coulomb square per Newton meter square, and this 0.112 into 10 to the power 6, and that's the flux. So which means it's going to be Newton per coulomb times meter square. Now let us take a look at how Team Gauss is solving this question. Oh, they simply say that the total flux phi is equal to q over epsilon naught. So that means this is 1 microcoulomb, 1 into 10 to the power minus 6 over 8.85 into 10 to the power minus 12, and the answer is 0.112 Newton per coulomb times meter square. So 1 point to each team. It seems that they've just cheated because they did not solve anything. So anyway, let's go on to the next question now. So 1 point to each team, 1 to team A and 1 to team B. Now the next question says that the charge has been shifted to one end. Let's say the charge is placed over here. It's the same charge of 1 microcoulomb, and the spherical surface is the same, that has a radius of 1 meter. Now you have to find out the flux in this case. Team A is once again finding the field at each point of the sphere, and then they will also have to multiply it with the area element to find out the total flux. but now it's going to be a little more difficult because the electric field is not the same everywhere. The distance of points from this is different. So this time it's going to be tougher because the electric field is not the same everywhere, which means that they can't take the electric field out of the integral and simply add up all the area elements. So while they are doing this, let's take a look at how team B is solving the same question. They can't cheat because team A has not finished the question as yet. Oh, team B already has the answer. They're saying that the total flux phi is 0.112 into 10 to the power 6 Newton per Coulomb times meter square. And the answer is the same as the previous answers. The answer hasn't changed. And they say that the flux doesn't change because the same number of field lines are going to cross the area this time also. Let's say this is the charge of 1 microcoulomb and these are a few field lines. Now look at this surface which is enclosing this charge. Now a certain number of field lines are emanating from the surface. Let's say we move this to any position as long as the charge is inside the sphere. So in that case what happens? The same number of field lines are going to cross the sphere. Say this is like this, then the same number of field lines are crossing the surface. You can actually see that the number of field lines crossing the surface doesn't even depend on the shape of the surface. See, even if you place a different surface which has a different shape, whatever might be the shape of the surface, it doesn't matter. In each case, the same number of field lines are crossing the surface. This question makes it 2 points for team B and 1 for team A. Moving on to the third question now. We have to find the electric flux through the spherical surface if charges of -2 microcoulomb and +1 microcoulomb are placed over here. Team A is planning to find the flux first due to the positive charge and then due to the negative charge and add the two up. Perfect. They have now learned from the previous question that the flux is not going to depend on the shape of the surface or where you place the charge with respect to the surface, as long as it is inside the surface. And the flux due to each charge is going to be Q by epsilon naught. So they're not going to waste any time integrating to find the flux. Now you see, for a positive charge we have an outward flux. The flux is in the outward direction, and for a negative charge the flux is inwards. The field is in the inward direction for a negative charge. Now one way of looking at this is, say you have an area element dA and this is the direction of the area element. Now if the electric field is in the same direction, then the angle phi between the electric field vector and the area element is going to be less than 90 degrees, which means that E dot dA, which is equal to EA cos phi, which is equal to EA EDA in this case, cos phi, is going to be positive. This means that an outward flux is positive and an inward flux is negative. See, suppose this is an area element. Say we consider the same area element dA and the field is in the opposite direction. Now if the field is in the opposite direction, then this angle between the electric field and the area element is going to be more than 90, and cos of an angle which is greater than 90 is going to be negative. Greater than 90 and less than 180 is going to be negative. So the flux, when the flux is inwards, it's going to be negative. They're right, but they're taking a lot of time doing all this thinking. Let's see. What about Team Gauss? Team Gauss has already answered this question long time back. They said that the total enclosed charge is -2 and +1, which is -1 microcoulomb. So the total flux is going to be the total charge enclosed, which is -1 in this case, over epsilon naught, and this once again works out to be 112 into 10 to the power 6 Newton per coulomb times meter square. So Team Gauss seems to have beaten Team Coulomb once again. Now Team Gauss, Team B has 3 points and Team Coulomb, which is Team A, has 1 point. Come on Team A, you need to buck up. Moving on to the fourth question. You have to find the flux through this surface if a charge of 0.5 microcoulomb is placed outside the surface. Team A discusses that the flux that enters the surface also leaves the surface. Hence, the net flux through the surface is 0. Fast work, Team A. Team B says that we only consider the charge which is enclosed by the surface, and since there is no charge enclosed by the surface, so when you look at this, Q by epsilon naught, and since Q enclosed, this is the Q enclosed is 0, so this is 0 by epsilon naught, so this is 0. Now since Team A answered this question first, so they get 1 point for this question. Now Team A has 2 points and Team B has 3 points. Now for the final question, and this is for 2 points. Consider a completely random closed surface and 3 charges which are placed inside it and a neutral metal piece. And 1 charge of 0.5 microcoulomb is placed outside the surface. What is the total flux through the surface? Let's see how Team A solves this. They add up the total charge. So the total charge is +3 and -3, which adds up to 0. They do not include the external charge. They do not include the metal piece because it is said to be neutral. So the charge on it is going to be 0. They know that they don't have to bother about the shape of the surface because the flux is going to be the same as long as the same charges are enclosed, and quickly give the answer as the net flux equals 0. Let's see what Team B says. Oh, it seems Team B did not listen to the question carefully. So they do not know the charge on the metal piece is 0 because the piece is neutral, and they have not been able to answer this question. So now for the final result. Team A is 4 points and Team B has 3 points. Slow and steady wins the race. So this brings us to the end of the quiz. I think Team B knew Gauss's law all along, whereas Team A picked it up while answering the questions. Let us first summarize what is Gauss's law. Gauss's law states that the total electric flux phi is equal to integral E dot ds, or you could use dA. So the total electric flux phi through a closed surface, this indicates a closed surface, is equal to Q over epsilon naught, and this Q is the enclosed charge.